The first unambiguous exoplanet discovery by the radial velocity method came in 1995, when 51 Pegasi b was discovered. Here's a graph showing the velocity of the star 51 Pegasi, taken over dozens of orbits, and then added together to show what a single orbit looks like. You can see that the star is moving towards and away from us in a regular pattern, demonstrating that it's being pulled back and forth by a planet. From the way the speed changes, we can tell that this is an 0.5 Jupiter mass planet, about 50% more massive than Saturn. But notice the time axis on the bottom. The orbit period for this planet is just a few days. In comparison, Mercury takes 88 days to move around the Sun. So 51 Pegasi b must be incredibly close to its star. This turns out to be the model for many of the exoplanets that have been discovered. After 1995, exoplanet discoveries steadily mounted, dominated by groups using radial velocity methods. This graph shows new exoplanet discoveries by year, from 1995 to 2008. By 2008, several hundred exoplanets had been discovered. However, these discoveries posed a big problem. The early exoplanet discoveries were mostly hot Jupiters, like 51 Pegasi b, much larger than Earth, and even closer to their host stars than Mercury is to our Sun. This was surprising. Our solar system has nothing like a hot Jupiter. For the people who were doing the observing, this wasn't such a big surprise. We've already seen that radial velocity is most likely to find large planets that are very close to their stars. However, this is very different from one of the big trends in our solar system, where giant planets are all very far from the Sun. So it raised important questions about how these planets formed. We'll come back to these questions in the next chapter when we talk about solar system formation. Hot Jupiters were the first big accomplishments of exosystem astronomy, and through the early 2000s, excitement remained high as improved technology detected smaller and smaller planets in larger and larger orbits. But it still wasn't enough to find planets that were more like the Earth, and the selection effects were large enough that it was hard to tell what was normal, solar systems like ours, or ones with giant planets close to their stars. All that changed in 2009 with the launch of the Kepler Space Telescope. In this picture, you can see it as the large orange, black, and white object being lifted into its vehicle in preparation for launch into space. For scale, notice the technicians in the white suits. The Kepler telescope uses the transit method to search for exoplanets. Remember that even if all stars have planets, most of these systems won't be lined up so that the planets pass in front of the star. So most stars you look at won't show any transits. The Kepler mission gets around this by looking at an unusually large part of the sky in a single field of view for a telescope like this, about 100 square degrees, or about 1/400th of the whole sky. This is about the area covered by your own hand's width at arm's distance, and it's 100,000 times bigger than the field of view of the famous Hubble Space Telescope. During the main Kepler mission, the telescope steadily observed one single field in the direction marked by the yellow cone in this picture. Kepler can get good observations of Sun-like stars up to about 3,000 light-years away. So the Kepler search space contained about 250,000 observable stars. 100,000 of these are stable enough to be useful targets for Kepler. By looking at this large number of stars, Kepler had a good chance of seeing transits.
Prior to Kepler, a modest number of planets had been discovered using transits, but Kepler used transit techniques to become the most important discoverer of exoplanets. In a previous slide, we saw the data through 2008. It's in blue, and all other data besides Kepler continues to be graphed in blue. The Kepler discoveries are graphed in orange, showing how much this single mission adds. But this graph is current only through February 25 of 2014. Click on the link to see how that data changed on February 26, 2014. See how the animation resizes the scale for all that new data? The yellow data adds 715 new confirmed planets, giving a total of 961 confirmed Kepler planets, over half the planets known to humanity. The trick to the huge growth in Kepler data is the realization that systems that look like multiple transiting planets are extremely unlikely to be anything other than planetary systems. Nothing else in nature that has the geometry of a multiple transit system could be stable enough to last more than a very short time unless it really were a system with multiple planets orbiting a more massive center. A system of multiple stars that started with the same layout would crash together or fly apart almost instantly. Kepler has found many systems of multiples, so it's great to have this efficient way of confirming their planetary status.
When we think of the Kepler results as a whole, we arrive at some extraordinary conclusions. Impressive as they are, the current confirmed planets are only part of the Kepler story. As of 2014, there are thousands of planet candidates in the Kepler data stream, and the astronomers doing the data analysis are confident that about 90% of them are likely to be confirmed. So it's safe to say that several thousand Kepler planets will be confirmed by the time the mission is complete. As we've already said, transits can only be detected in edge-on orbits, so the Kepler discoveries are only a small fraction of the systems in the search space. Allowing for orientation, most stars have at least one planet. And because so many systems are multiple, planets are actually more common than stars. This is the first time in human history that we can say this with any confidence.
Kepler's goal isn't just to find a lot of planets. It's specifically to find Earth-like planets. First, we need to define what we mean by Earth-like. In this case, it means approximately Earth-sized, because a much smaller planet would have gravity too weak to hold an atmosphere, while the gravity of a much larger planet would attract gases from the planetary nebula and become a Jovian, with a deep atmosphere and no solid surface. An Earth-like planet also needs to be the right distance from its host star to be at the right temperature. Because all life we know needs liquid water, astronomers use the term habitable zone to describe the region in which a planet could have the right temperature for liquid water to remain on its surface. We'll talk more about the habitable zone later in the course when we look at life in the solar system. These are the sizes of all exoplanets known as of February 26, 2014. The blue data is everything known up to that date, and that tall blue bar for Jupiter size and larger gives you a sense of how strongly all detection methods select for large planets. Whether detection depends on mass or radius, it's simply easier to find big things than little ones. The orange color adds the 715 planets that were announced in February 2014. It shows that Kepler is better at detecting planets of smaller sizes than previous methods, and already it gives us a more representative, less biased count of the distribution of exoplanet sizes. Notice that Kepler has found many examples of a kind of planet entirely lacking from our solar system, larger than our Earth, but smaller than Neptune. By carefully analyzing selection effects in Kepler's data stream, astronomers have made the current best estimate of the true distribution of exoplanets in nature. Notice how different this is from the raw data we saw on the previous slide. The distribution is nearly the opposite. Jupiters are not common, they're rare. Even Neptunes are rare. Earths are much more common, but there are also large numbers of super-Earths and mini-Neptunes. This is a surprise because our solar system has no planet in this size range. It's also a puzzle because astronomers still debate what such a planet might be like. If any category is still undercounted, it will be the planets Earth size and smaller. Though this graph shows the estimate that emerges from the best analysis of current data, the possibility remains that Earth and smaller categories will prove the most numerous of all. Such a distribution would be an example of a power law, a distribution with the largest counts in the smallest categories. This would be theoretically very satisfying. Power laws are so common in nature that we tend to look for a special reason whenever we don't find.
A power law describes a distribution with the largest counts in the smallest categories. Power laws are common in a wide variety of situations. For example, there are many more small rocks than large ones. There are many more small businesses than large ones. In your group, brainstorm another example of a power law. It may be from any area. Explain in what way it follows a power law. Also, give an example that is not a power law and explain why it doesn't follow this pattern.
With so many exoplanets now known, we have time to explore only a few. Kepler 10b was the first planet found orbiting the star now called Kepler 10. It was discovered in the first 8 months of Kepler data and announced in January 2011. It's only 1.4 times the radius of Earth. At its discovery, it was the smallest exoplanet found. It's also the first exoplanet we know, because of its density, to be a solid planet with a rocky surface, rather than a gas or water world. It orbits so close to its host star that it should be tidally locked, with the same side always facing the sun. Intense sunlight melts the rock of its dayside surface. Even smaller planets have since been found. Kepler 37b, announced in February 2013, is only slightly larger than our Moon. There are also much larger planets that have been found to be rocky as well. In fact, another planet in the same system as Kepler 10b is Kepler 10c. This planet is dense enough to be rocky, even though it's 17 times the mass of Earth. That's a terrestrial planet that is comparable in mass to Uranus or Neptune.
In 2011, Kepler 22b became the first planet confirmed in the habitable zone of a Sun-like star. The planet is 2.4 times the radius of Earth. When it was confirmed as a planet, it was also the smallest found in such an orbit. Though its density is not known accurately enough to be certain, it might be a water world with very deep oceans, or possibly a thick atmosphere over a small, rocky core. Either way, it is a promising prospect for life. It became one of Kepler's best known and most frequently illustrated planets. The accompanying artist's conception shows what it might look like if it had a cloudy atmosphere above an ocean layer.
Circumbinary systems are systems in which a pair of stars orbits each other and one or more planets orbit the stars. Of course, some of the appeal here is sheer weirdness. Wouldn't you like to admire a double sunset from the vantage point of such a planet? More seriously, as we have come to understand that as many as half of all stars are binaries, we appreciate the importance of knowing whether binaries can host planets. Decades ago, astronomers were skeptical, suspecting that binaries with gravitational tugs towards more than one center provided too unstable an environment to form and hold planets. However, the discoveries of Kepler 16b, Kepler 34b, Kepler 35b, and the Kepler 47b and 47c system show that some binaries are indeed hosts. Perhaps a Luke Skywalker really is out there gazing at the double suns of a Tatooine.
While Kepler has only recently reached the stage of observing long enough to find planets in the habitable zone of Sun-like stars, It has already found Kepler 186f, an Earth-sized planet in the closer habitable zone of a smaller, cooler red dwarf star. While its dwarf star host means that it can't be called Earth's twin, this planet has been called Earth's cousin. It's likely to be a rocky world with geological similarities to Earth, and depending on its atmosphere, it might be able to sustain liquid water on its surface. Its F designation indicates that it's a member of a complex system, as are many in the Kepler data set. Since Kepler 186f is only 500 light-years away, very close by galactic standards, its discovery suggests that Earth-sized habitable zone planets are extremely common in our galaxy. It's impossible for us to look at all known exoplanets, or even all the exciting ones. So instead, we'll look at this visualization by Daniel Fabricki from the Kepler science team. You can click on the image to get a link to the animation. It's called the Kepler Orrery, and it shows the relative sizes and periods of the orbits and the relative sizes of the planets in the multi-transiting planetary systems discovered by Kepler up to November 2013. Our solar system is shown in gray in the top left, and in the exosystems, colors go by order from the star. Can you find the most colorful system, the 7-planet system KOI 351? Remember, what you're seeing isn't just an entertaining picture. Every one of those systems is validated data. It stands for a solar system that really exists in nature.
In 2013, after 4 years of data collection, the Kepler mission lost the second of 4 reaction wheels used for pointing control. A second K2 mission is taking data with diminished pointing accuracy, looking at different parts of the sky. Successor missions will launch soon. The Transiting Exoplanet Survey Satellite, Tess, in 2017, and the James Webb Space Telescope, JWST, in 2018. Tess will carry an array of wide-field cameras and will be able to detect the masses, sizes, densities, and orbital parameters of small planets orbiting brighter stars near the Earth. Test data will be used to select targets for more detailed studies by JWST, which will be optimized for near-infrared imaging and spectroscopy, ideal tools to explore the atmospheres of planets. Atmospheric information is what we really need to tell us whether a planet is truly habitable. This information should answer some of the most tantalizing questions raised by exoplanet discoveries. Which exoplanets are rocky, watery, or gaseous? Have they cooling clouds or heating greenhouse effects? The proximity of Tess and the JWST mean that another Earth, a planet of the same size and composition and atmosphere, at the same distance from a sun-like star, is a discovery to expect in the next 5 to 10 years. Possibly it's already there, awaiting discovery, in data we already have. When we find it, there's a good chance that we will be able to tell if it's inhabited. For the first time in human history, we may be able to answer a question humans have asked for centuries. Are we alone, or do we live in a universe rich with other life?
Remember the questions about exoplanets that your group wrote down? Go back and see if we answered them. If not, you might want to check the links on the next page.
Exoplanets are a hot topic in astronomy right now, and there's frequently exciting news about them. To keep up with it, 2 good links are the official Kepler site, kepler.nasa.gov, and Wikipedia's exoplanet article.